In this module, we'll look at using truth tables to determine what kind of individual sentence we have in our language. There are three kinds: logical truths, logical falsehoods, and contradictions. So here we have Gottlieb Frege, German mathematician and logician, to tell us what a logical truth is. Logical truths are sentences that have a form, underlying logical structure, such that they cannot be false under any assignment of truth values to the constitutive simple statements. So they're always true, no matter how the world turns out. So when we want to test for logical truths, which are sometimes also called tautologies, one simply fills out a truth table, and we look under that main connective, the last connective that we look at in that column. If it's a logical truth, then for every row, every way the world could be, that statement will be true. So let's look at a couple of examples. Here we've got two different formulas on two different truth tables. We fill in our guide columns, transfer those over to the individual simple statements. Let's start on the right-hand side. We'll start with the innermost logical connectives. Start with the tilde. Then we'll do our horseshoe. Then we'll do the tilde on the outside. And then we'll do the main connective, the last connective, the dot. Under that dot, we have one false and we have one true. That statement isn't always true. There's at least one way for it to be false, so it's not a logical truth. Let's look at the other formula. Here we just have our horseshoe. Fill in the truth values there. Only way to make a conditional statement false is if the antecedent is true and the consequent is false. So both of those rows are true. There's no way for the world to be that makes the statement false, and hence it's a logical truth. Our next kind of statement is a logical falsehood. And this is George Boole, discoverer or creator of Boolean algebra, a mathematician and logician. He's here to tell us about logical falsehoods. Logical falsehoods are statements that have a logical form, an underlying structure, such that they cannot be true under any assignment of truth values to the constitutive simple statements. And so if we want to test for logical falsehood, or sometimes it's called a contradiction, we fill out our truth table, we look under that main connective, the last connective that we look at, and if it's always false, it is a logical falsehood or a contradiction. If there's even one row where it's true, it is not a logical falsehood. So let's look at a couple of examples. Here we have this formula. We fill out our guide columns under our letters. We start with the innermost connectives. In this case, they're both dots. Then we go to our outer connectives. We do the tilde first, then the dot, and under that dot, the last connective that we do, the main connective, it's false, 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 false. This formula is false no matter how the world turns out, no matter what assignment we make to those simple constitutive simple statements, P and Q, it's always false. So it's a logical falsehood or a contradiction. Let's look at a different one. Let's look at another example of a statement that's not a logical falsehood. So here we have a different formula. Again, we copy our guide columns. Again, we work from the logical connectives in the most number of brackets, again, both dots. So here's one, here's two. Then we go to the logical connective in the least number of brackets, and that is our triple bar. Triple bar says, I'm always true when they have the same truth values. I'm always false when they have different truth values. So we fill that out, and it's always true. So this statement isn't a logical falsehood because it's possible for it not to be false. Instead, this statement is what? That's right, it's a logical truth. Let's turn now to our final kind of individual statement, contingent statements. Here's Rudolf Carnap. He's here to tell us that contingent statements are statements that vary in their truth or falsity. Sometimes they're true, sometimes they're false. So different assignments of truth values to their constitutive simple statements can result in different truth values for the entire statement. So how do we test for contingent statements? Just as before. We fill out our truth table. We look under the last connective, the main connective. If there's at least one row where that statement is true and at least one row where that statement is false, that statement is a contingent statement. So suppose we have this statement. Copy our guide columns. Use the connective inside the most number of brackets first. That's our horseshoe. Only false if the antecedent is true and the consequent is false. So, voila. Then we go out to that tilde, the last connective, the main connective. That tilde is going to reach out and grab everything in our brackets here. So we look under our horseshoe and we use our rule for the tilde. True, it's false. False, it's true. True, it's false. True, it's false. So now we look at this column, the truth value for this whole formula, every different way the world could be, and we see there's at least one way for it to be true and at least one way for it to be false. And so this is a contingent statement. In the next module, we'll turn our attention to using truth tables to look at relationships between individual statements in our logic.